Okay, hello everyone and welcome back to your YouTube channel. And welcome to this very short but interesting video related with single cage induction motor. And today we have here an statement. We have a 3-phase 400 volt 50 hertz 250 horsepower 4-pole induction motor. And here we have the data, the following equivalent circuit parameters. You have here the rotor, the stator resistance, the rotor resistance, the stator reactance, the rotor reactance, and also the magnetizing branch. And this motor is directly connected to a 3-phase supply. You can see 400 volts, 50 hertz. And we want to obtain the synchronous speed of this induction motor, also the synchronous speed, but in this case in radians per second, also the Thevenin impedance from the stator side, and also the Thevenin voltage from the stator side. And let me put this one in black here, and also the starting torque. And here we have the slip at the pull-out torque, and then the mechanical rotor speed to the full pull-out torque, and finally the breakdown or pull-out torque in Newton per meters. Okay. Let me clarify this one. Yes, this calculation is in Newton per meter. Perfect. So then we have a condition over here. Assume that the motor torque is proportional to the slip near to the synchronous speed, and neglect the rotational losses. So now we are given here a condition, the motor drive a load of 1.8 Newton per meter. Determine the slip at this condition, yes, the low condition. Then the mechanical or rotational speed in radians per second. And finally, the rotational speed in RPM. So this is very simple. Today, as you can see, we are using a MATLAB live script. As you can see over here, we are including first the parameters. You can see we are using 4 poles, 50 hertz, 250 horsepower. The line-to-line voltage is 400. We have here stator resistance, rotor resistance, stator reactance, rotor reactance, and finally we have here the magnetizing branch. So the very first question is very simple, is related with the synchronous speed. And you must remember the synchronous speed is defined by the frequency and of the signal applied to the stator, and also to the number of poles at the winding. So this equation over here, what it's telling you is that the synchronous speed in RPM is numerically 220 multiplied by the frequency in hertz and divided by the number of poles. So when we put the number together, we obtain here the amazing results. The rotational speed is 1500 RPM. So the next question is, okay, but we want the synchronous speed now in radians per second. So in radians per second, this is calculated using just a very simple conversion. We multiply by 2 pi and divide by 60 in order to convert to radians per second. And when we put the number together, you can see here the answer for question B. We are talking about 157 something radians per second. Now you must remember something very important when you are working with 3-phase devices or 3-phase components. The nominal voltage is a line-to-line voltage. So the 400 volts that we are given here, this voltage is a line-to-line voltage, so we need to convert into line to neutral. And the reason that we need to convert that voltage into line to neutral is because all of you must remember this amazing model, because this is the circuit model for the induction motor. And in this equivalent model, this is a single phase equivalent model. You must remember that all the quantities are referred to the stator, and the stator is connected between line to neutral. So that is the reason that we are converting these 400 volts line to line into line to neutral, equivalent to 230.9 volts. So the next question is, we want to know the Thevenin impedance, but in this Thevenin impedance, we are interested on the Thevenin impedance on the stator circuit. So first step is this resistance and this reactance on the stator. We are converting then into the impedance. So the impedance at the stator, here this series branch is basically 0.59 plus J 0.10 ohms, okay? So the next step is calculating the Thevenin impedance, but the Thevenin impedance, all my students must remember, we close the circuit here, we have this impedance in parallel with the magnetizing branch, and that is what I am telling you over here, yes? Over here you can see that we are defining the parallel, the parallel between Z1 and also JXM. That is the Thevenin impedance between the point A and point N. So basically we are solving here the parallel between Z1 and JM. We obtain here the Thevenin impedance. I am presenting in rectangular and in a polar form, but also the Thevenin resistance is 0.58 and the Thevenin reactance is 0.13. So next step is I need to know the Thevenin voltage across those points over here, A and N. And to do that, what I need to do is a voltage divider, because we know the terminal voltage, and the terminal voltage in this case is the line to neutral volt, and that is 400 divided by square root 3. We multiply by the magnetizing branch, 11 ohms, and divide by the total impedance, in this case the stator plus the magnetizing. So as you can see, we have a Thevenin voltage. Here, this is a complex number. On the top, you can see the rectangular representation, and here you can see the polar representation. And using the polar representation, I can tell you that the Thevenin voltage is 228.36 volts, and the angle is 3.0 degree. Now the question is, how much is the induced torque? Well, the induced torque, if you go back to the slides related to the class, you will find this very large equation over there, and this equation is basically giving you the torque at any possible slip. However, this equation can be simplified, for instance, if we are calculating the starting torque. At the starting condition, you must remember that the rotor speed is 0, so the slip is maximum and is equal to 1. So in this equation over here, let's call this the equation number 1. At the equation number 1, when I substitute the slip equal to 1, You can see that here there is some simplifications and we obtain this beautiful equation number 2. That equation number 2 is also included in your classes, in your theory classes, and also it was explained over there. But now what we are doing is just basically substituting the slip for the starting condition into the equation. So the starting torque, when you put together all the numerical values, and remember here we need to use is the absolute value of the Thevenin voltage because this is a complex number. So the starting torque is 127 Newton per meter. Then the second question over here is, well, if you consider the pull-out torque, what is the slip for that very specific pull-out torque? And again, if you go to the theory, I already showed you that there is an equation. That equation is basically telling you the value for the slip when the torque is the pull-out torque. And that equation depends on the rotor resistance and the Thevenin impedance. So when we substitute the numbers over here, we obtain the most important answer, and this is the slip for the pull-out torque. If you know the slip for the pull-out torque, it's very simple to obtain the rotational speed. And that is because if you look to this equation number 4, what is telling you, that equation, what is telling you is that basically the mechanical speed is related to the slip by this equation. 1 minus slip multiplied by the synchronous speed. The synchronous speed we already calculated, 157 radians per second. So the rotational speed will be now, as you can see over here, will be 106.41 radians per second. So next question is to calculate the maximum torque. And that maximum torque happens at this very specific slip. So basically what we are doing is taking equation 1 and substituting the slip calculating using equation number 3. And when we do so, we obtain that the maximum torque, also known as breakdown torque, and in some books also pull-out torque, that is basically 196.6 Newton per meter. As you can see over here, the starting torque is only 127, but the maximum torque, the pull-out torque, is 196. And that is clear because if you remember the shape of the torque speed characteristic, this value is typically larger than the starting torque. The final part of this solution is basically we are given a mechanical load, and this mechanical load is represented using torque, in this case 1.8 Newton per meter. So this is a very small load because if you consider the maximum torque here is 197, so we are talking about around 1% or 2% of the maximum torque. So we can do something quite simple. If we assume that the slip is very, very small, so we can make some simplifications saying that the resistive part is larger than the reactive part. And also the rotor circuit is larger than the Thevenin circuit. So we can simplify a lot the equation, and this will be the equation number 6. And that equation is basically telling you the value for the linearized model of the torque for this condition. And when you put the numbers over there, you can see that the slip is extremely small, is 0.0011. So now what we can do is to calculate the rotational speed in radians per second using the equation that we already defined, and that equation is related the synchronous speed with the slip. And you can see that the rotational speed is almost near to the synchronous speed, is 156.9 radians per second. And you can see here also the calculation of the rotational speed using RPM. So we are converting, multiplying by 60, dividing by 2 pi, and the rotational speed in RPM is 1498 RPM. So as you can see, for this low condition that is extremely small compared with the maximum torque, we are having a very small slip. That means that the rotational speed is close to the synchronous speed. And as you can see, the synchronous speed was 1500 RPM. And when we have 1.8 Newton per meters, this rotational speed is 1498.2 RPM. But remember, we were able to solve this problem in a very simple way because we know that this load is extremely small, and we can do some simplifications and obtain equation number 6 that allow us to simplify a lot the calculations and obtain the solution. What I suggest to my dear students is that they go back to home and they use the equation number 1 in order to obtain the slip for given a very specific torque. For instance, in this case, include over here 1.8 Newton per meter and calculate the value of the slip. If you are using the equation number 1, you will get a more complicated equation defining the slip, but you will find the very specific and full detail solution. I mean, not the simplified solution. So I highly suggest my students to try this at home. Well, this is the very end of this video. I hope that you enjoy the use of this MATLAB Live script. I hope that you enjoy the possibility of calculating several points of the operating characteristic of the induction machine. I mean the torque speed curve. And also that you understand that when we are working close to the synchronous speed, we can simplify the equations, we can linearize the model, and we can obtain easily numerical solution. Finally, if you like this video and you would like to stay in touch, here there are some links for our community. Please stay in touch, and I will be extremely happy to help you. Thank you very much for watching, and this is all for today's video. Thank you, and I will see you very soon. Bye now.